Welcome to The Explainer. Have you ever just stopped to look around and wonder why the world is built the way it is? I mean, really thought about it. Why do certain things flex? Why do others just snap in half? And how do engineers know exactly what materials to use when they're building a massive skyscraper versus, say, the smartphone in your pocket? Well, today we're going to look right past the surface and decode the actual building blocks of reality.
Let's kick things off with a little mystery. It seems super simple, but it actually reveals the literal secrets of the universe's building blocks. Think about your kitchen for a second. If you drop a ceramic coffee mug on a tile floor, it absolutely explodes into a dozen sharp pieces, right? But if you accidentally knock a heavy metal pot off the stove, it hits the ground with this loud clang and, at worst, you get a little dent. So why is that? They're both solids, they both feel incredibly hard to the touch, yet they react to the exact same drop in totally opposite ways. The answer isn't about how they fell, it's all about what is happening on a microscopic, atomic level.
Basically, everything engineered around you falls into one of four distinct families. We've got metals, which are known for high strength, polymers, which give us low density and low cost, ceramics, which are incredibly hard and heat resistant, and finally composites, which offer this synergistic high performance. Today, we're going to build a really intuitive understanding of why they behave the way they do.
So, let's dive right into Section 1, Metals, the electron sea.
Okay, I absolutely love that phrase, electron sea. When we think of a solid piece of metal, we usually imagine something completely rigid. But atomically, a metal is actually more like a crowded dance floor. The positive ion cores are arranged in this neat little grid, a lattice, but their outer electrons are completely free to roam around. They're delocalized. So when that metal pot hits the kitchen floor, instead of snapping under the pressure, the metal bends, the positive ions shift their positions, and this flexible moving sea of electrons just flows right along with them, keeping the whole structure glued together without breaking. And that is exactly what gives metals their ductility. Now, obviously, not all metals are created equal. Just think about the sheer difference in density for a second. Iron is incredibly dense, coming in at nearly 7,900 kilograms per cubic meter, but then you have titanium, which is almost half that weight, and aluminum, which is even lighter, at just 2,700. Visualizing this really builds an instant intuition for why aerospace engineers choose specific metals. I mean, you definitely wouldn't want to build an airplane out of solid iron. It would be way too heavy to ever get off the ground.
And these unique metallic properties are exactly why we rely on specific metals for specific jobs. We use carbon steel, which is an alloy of iron and carbon, to hold up skyscrapers and build our cars. But when we need something that can survive the absolutely scorching extreme heat inside a jet engine, we turn to nickel to create superalloys. We use copper for wiring because, well, that sea of electrons we just talked about makes it an unbelievable conductor of electricity. And titanium, its incredibly high strength-to-weight ratio and corrosion resistance make it perfect, not just for aerospace, but for biocompatible medical implants right inside the human body.
Now, what happens when we swap out that fluid electron sea for long, tangled strings? That brings us to Section 2, Polymers, giant molecular chains.
So if metals are a neat grid floating in an electron sea, I want you to picture polymers as giant tangled bowls of spaghetti. Polymerization is just the process of linking repeating structural units, we call those monomers, together using really strong covalent bonds to create massive macromolecules. Try to think of polymers not as solid continuous blocks, but actually as giant tangled chains of molecules. Because these chains can slide past one another and uncoil, polymers are often super lightweight and highly flexible.
Engineers actually use a really simple equation for this. And hey, don't let the math intimidate you, the logic is super straightforward. The total molecular weight of a polymer is basically just the number of repeating links in the chain, that's the N, multiplied by the weight of a single monomer link. That's it. Engineers can literally design a material's physical properties just by controlling N, by deciding exactly how long these molecular chains get to be.
This completely challenges that old assumption that plastics are weak, right? These tangled chains are unbelievably versatile. For instance, an amorphous thermoplastic called ABS is responsible for the incredible rigid toughness of a Lego brick. Then you have polycarbonate, which has such high optical clarity and impact resistance that it's literally used to make bulletproof windows. We even have PLA, a biodegradable polymer used for medical sutures that harmlessly dissolve right in your body. And elastomers like natural rubber that can stretch hundreds of times their original length and snap right back into place.
Moving right along to our third block, we encounter materials that flat out refuse to bend and therefore must shatter. Section 3, Ceramics, the unbreakable bonds.
All right, this brings us right back to that shattered coffee mug from the beginning.
Unlike metals with their forgiving sea of electrons or polymers with their flexible spaghetti chains, ceramics are locked in incredibly strong, rigid, and highly directional ionic and covalent bonds. There's absolutely zero flexibility here. Literally no dislocation motion is possible. So because their atoms are locked in this extreme grid, ceramics can withstand massive, intense heat without ever melting. But hit them with a hammer or drop them on the tile floor, and because those atoms physically cannot slide past each other to absorb the energy, they just snap instantly.
To understand just how incredibly rigid these bonds are, engineers use something called the Pauling equation. Again, focus on the big idea here, not just the symbols. This equation lets us calculate the exact fraction of a bond's ionic character based on the electronegativities of the two elements involved, which is really just a fancy way of describing their underlying pull on electrons. It's basically a way to mathematically prove exactly how locked in and rigid the atomic structure of a ceramic is going to be before it's even manufactured.
Because of that extreme rigidity, ceramics are for way more than just your morning coffee. Their insane hardness makes them the ultimate shield. We use boron carbide to create armor plates that literally stop bullets. We use silicon nitride for high-temperature engine bearings, and zirconia for dental crowns that are tough enough for you to bite down on hard food for the rest of your life. We even use aluminum oxide and diamond as industrial cutting tools because they are, quite literally, among the hardest materials known to humanity.
Finally, what if nature's base materials just aren't quite good enough on their own? Well, that brings us to Section 4, Composites, the ultimate team-up. When engineers need something impossibly strong but also incredibly light, they create a composite. It's essentially forcing two totally different materials to team up. But the real secret here is that they don't dissolve into each other. They retain their individual identities, and by working together, they achieve synergistic properties, basically covering up each other's weaknesses to create something way greater than the sum of its parts.
Let's think about how this physically works. In a fiber-reinforced composite, you generally have two distinct parts playing together. First, you have a continuous block called the matrix, often something like an epoxy polymer. The matrix's entire job is to bind and protect the second part, which are the fibers suspended inside of it. These fibers are the actual muscle. They are what carry all the heavy physical loads when the material is being pulled or stressed.
Now, to actually design these hybrid materials, engineers can't just cross their fingers and guess. We have to precisely calculate how much of the team's total strength is coming from the reinforcing fiber versus the protective matrix. This foundational concept in materials science is known as the rule of mixtures.
And here is that rule of mixtures in action. This equation helps us predict exactly how stiff the final composite material will be. It's a formula that simply combines the stiffness of the fiber and the matrix scaled by their volume fractions. Actually, it's really just a weighted average. If you know exactly how much fiber you're putting into the mix, you can perfectly predict the strength of the final product before you even make it.
You really see this magic at work when you compare two of the heavy hitters. On one hand, you have carbon fiber reinforced polymer, or CFRP. It is incredibly light and has immense tensile strength, which is exactly what gives Formula One cars and aerospace structures their extreme performance. On the other hand, you have glass fiber reinforced polymer. It's a bit heavier and not quite as strong, but it's incredibly durable, electrically insulating, and way cheaper, which gives boat hulls and massive wind turbine blades excellent performance at a fraction of the cost.
So we've broken down the physical world. Now that you know the secrets of the malleable electron sea, the flexible giant molecular chains, the unbreakable ceramic bonds, and those ultimate composite team-ups, take a second and look around you right now. How many of these hidden engineering marvels are sitting in the room with you? And more importantly, as engineers continue to manipulate these atoms in entirely new ways, what impossible materials are they going to dream up next? Keep questioning what everything is made of. Thanks so much for joining me on The Explainer.